Hello, everyone. Welcome back to the AAS YouTube channel. And this is the continuation of the good stuff, the AAS Journal Author Series. And I'm very happy to have Jason Rhodes with us today. Hey, Jason.
Hello. Thank you for having me on the show.
Well, it's really great. I think it's a really lovely article. It's out there, let's put it that way. So we'll get to that. Very cool. So what is your geolocation?
I am in Altadena, California, which is right by where I work, NASA JPL.
Ah, very nice. Very good. So no snow there.
No, it's actually pretty nice today.
Yep. So I'm in Phoenix, and we're doing just about as well. It's very nice today. Very pleasant winter, which is, I guess, one reason why people live here. So are you guys, are you back in JPL? Is with the pandemic going, or are you sort of mainly working from home these days, or what's the?
No, so what JPL has done, and I think largely what NASA has done, is they've had the essential people who need to be on lab. And the way I describe that is people who need to touch something in order to get it prepared to go into space. Mm-hmm. So as a scientist, I only really need to touch my computer. And so we're at home. So of the about 6,000 JPL employees, I think there's a bit over 1,000 that are working at various times at JPL and in various shifts. And there's a pretty strict protocol. I did go into my office once a couple of weeks ago to pick up some posters that somebody had put there, some promotional posters, and I had to fill out some forms. But other than that, I am working alternately from a desk I have in my bedroom, or I'm sitting here in my kitchen, and what you see behind me is actually the wallpaper in my kitchen. Okay. And my wife is also an astronomer, and so that's why we both have two places we can sort of work. If both of us have a video con at the same time, we decide who goes upstairs and who stays downstairs.
Did your wife also work at JPL?
Yes, my wife is also an astrophysicist at JPL.
Cool. All right. So Jason, what do you like to do for research in astrophysics?
So my background, what I did for my PhD is galaxy surveys. And towards the end of my PhD, I got into weak gravitational lensing, which is a technique for measuring the amount and distribution of dark matter using galaxy surveys. And that led me into developing missions to study dark matter and dark energy. So most of the past 15 or so years of my career has been developing space missions, including ESA's Euclid mission, which is set to launch in 2022 for study dark energy. NASA's Roman space telescope, Nancy Grace Roman Space Telescope, which until this spring was known as WFIRST. Mm-hmm. I'm the JPL project scientist for Roman, and one of its big pushes will be in studying dark energy. So I sort of alternate between doing science with current data and developing future missions.
Cool. And speaking of future, that will take us to this really lovely article, which, let me do the screen share here. The end of galaxy surveys. And Jason, take us away.
All right. Well, the idea here came out of a very short presentation I gave a few years ago at JPL. JPL has what's called a pitch day, where they select a few people to pitch to a panel some wild idea. And my wild idea at pitch day at JPL a few years ago was, let's measure every galaxy in the universe. Okay. And so this was not a pitch to astronomers. And so I kept it fairly simple. And somebody at JPL heard it and said, hey, that's a really cool idea. You should apply for this internal JPL funding and study this idea. And so that's what I did. I got a little bit of internal funding, and I put together this team of colleagues at JPL, including Eric Huff, Dan Masters, and Anna Nierenberg. And we started to think about what would it take to measure every galaxy. And one of the first things we came up with as we were doing that is the concept of a galaxy is a little bit ill-defined, and what does it mean to measure every galaxy? So
Right.
we went in a slightly different direction, and the direction we went in is what would it take to end the current era of galaxy surveys? And
Okay.
so when I talk about galaxy surveys, there's galaxy surveys going on from the ground, and of course, in space, we'll have Euclid and we'll have Roman in the coming decade, and we'll have LSST on the ground.
Yep.
And all of these are taking images and spectra of millions and even billions of galaxies. And so a common thing that we do in astronomy is we think about, okay, what's the next survey that we'll have to do after this one's complete? What comes next? And so we turned that on the edge and we said, not what comes next, but what's the last survey of this kind we would ever have to do?
Okay.
And so we picked a few science cases, and those science cases are dark energy cosmology, galaxy evolution, and studying supernova. And we said, using the current techniques for doing that with galaxy surveys, what would be the survey and therefore the telescope that would allow us to exhaust the information content in the universe for these probes of those science questions? Now, I want to have a bit of a caveat here that we're not advocating that this is the only or even the best way to answer these science questions. Really, what we set out to do was to say, all right, how much information is in the universe? Right. How much information is encoded in the positions, the shapes, and the fluxes of galaxies relevant to these questions?
Right. Okay.
So it's a fairly simple answer, or sorry, fairly simple question. And I don't think we're unique in thinking of this question. There have been other papers in the past that sought to figure out what is the ultimate galaxy survey. Partly because, of course, the universe, the observable universe, is both finite and has a beginning, and so you don't have to look back infinitely far in the universe to see the very first galaxies. So that's what we set out to do. Should we move on and I tell you how we did that? I'm happy to go through the paper.
Yeah, and that's what we want to do. We want to walk through this paper.
Okay. All right. So the first equation was just an equation for the signal to noise of a measurement. And what we said is we're going to make the measurements in the near infrared. And we chose the near infrared because that's the wavelength that current next generation space missions like Euclid and Roman are doing. We didn't necessarily say, again, that would be the best wavelength for answering these questions. We just said, okay, if we take to a logical conclusion of what we're doing and make these measurements in the near infrared at around 2 microns, this is the signal to noise equation we would use. And this table 1 gives a number of parameters for the survey and therefore the telescope. And some of these parameters, if you look there, things like the mirror diameter and the read noise, a number of pixels, of course, those are parameters we choose or would choose or our descendants will choose when they build this huge telescope. But some of these parameters are the ones given to us by nature. That is source flux. If we want to look at the furthest, faintest galaxy, that's going to be defined by whatever's out there in the universe.
Right.
And others are a little bit more nuanced. For instance, one of the interesting ones that we thought about was sky flux. How bright is the sky? Of course, this is given to us by nature, but depending on where we put the telescope, we can change that. We can change that value. And so that's one of the lever arms that we found. So this table lists, I think, really all of the relevant parameters for defining a galaxy survey as we were trying to do. And we made a few simplifying assumptions in doing this. we said, okay, let's say that the quantum efficiency of our detectors and our telescope is 1. That is, we're not getting any loss of photons. Now, we know that that's not going to be true, but the QE of current generation detectors is pretty high. And so we said, we'll make that assumption. We also make an assumption that things like dark current and read noise are 0. That's a bit more of a stretch. But again, in doing this, we've outlined the equations, how that would affect things. So we could go back, and if we don't have perfect detectors, we could go back and make those changes. But
Right.
for the purposes of the article, we set out to say, okay, let's say we have perfect detectors. And so I guess if we move forward a bit here, we're just then in equations 2 through 5, we're solving for the amount of time it would take to get to a certain signal to noise on an object, given the size of the telescope, the flux of the object, and so on. And for a measurement, we are saying we need to get to signal to noise 10. Again, that's just a choice that we made. And we made that choice because typically we find, for instance, in my field, weak gravitational lensing, that to measure the shape of a galaxy, we need about a signal to noise of 10. And so we found that to be a good way to start. And so then if we want to find out how long it would take to do a survey with a certain number of telescopes and size of telescopes, that's given by this equation 6. And so then what we did is if we move, well, let me just say equations 6 and 7 are both the time it would take to get to a certain depth in a survey. One is for if we had resolved objects, and one is for if we had unresolved objects, point sources. So we solved for both of those. But one of the things that we ended up doing later in the study, in the paper, is we said, well, we really want to get to a telescope diameter that's going to allow us to resolve these earliest, faintest galaxies, because if we want to measure their shape, we need to have those resolved. And so we make another pretty big caveat here in section 2.2 about redshifts and spectroscopy. And what I mean by that is, as we go through this exercise to define a final galaxy survey, we are saying, okay, we're going to take a measurement at 2 microns, but a single band. And anyone who does galaxy surveys knows that we don't need a single band. Depending on the science, we need a few bands at least to get a photometric redshift, or we need many bands, full spectrum, to get the full spectroscopic information from a galaxy. Yep. So this simplifying assumption, I think, unlike the one with the saying that we have perfect detectors, isn't sort of a small tweak. This could be a huge simplifying assumption, in that the numbers we get for how long a survey would take would need to, if we're only getting a single wavelength band, would need to increase by a few, or maybe even up to 1,000 if we want to get spectra for everything. So again, we are making some simplifying assumptions. But as I'll discuss later, when we come back to the end of the paper, we talk about what those assumptions mean for future technology. So if we go to then section 3.2, we talk about getting cosmology from galaxies. That's one of our 3 science cases that we're outlining. And for this particular science case, what we did is we said, we're going to keep getting useful information from galaxies in terms of their shapes, their positions, and how they're clustered up until the turnover in the luminosity function of galaxies.
Yes.
And we don't know, astronomers don't know where that luminosity function turns over. That is where there stops being more and more galaxies that are, smaller and smaller and fainter back in the early universe. And so what we've done is if we go on to the next page, we've made some, assumptions about that, and we define the turnover in the luminosity function at what we think is a reasonable assumption based on current research, but probably a bit on the optimistic side. And what I mean by that is if there's more and more galaxies fainter and fainter and further away, we would need a bigger telescope or a longer survey to get all of that information. So we make a somewhat, I would say, optimistic assumption about what where that turnover in the luminosity function is. And then we define here in equation 9, we say, okay, if that's where that turnover is, this is the size of those galaxies, this is the brightness of those galaxies. So we define sort of a scaling relation here for how long would it take to do this final cosmology survey. And what we said is we're going to want to do the survey in 10 years. And that's a number we chose, a fraction, a good fraction, but a fraction of a professional astronomer's professional career. And typically how long maybe a space telescope lasts. And so if I just walk through that equation, the N there is the number of telescopes. So of course, if we have more telescopes, it goes faster. NB is the number of distinct wavelength bands we want to do this in. And I mentioned that before. So if we need 4 bands to get photo Z, it's going to take 4 times as long, and so on. The A naught is the size of those smallest, faintest galaxies at where we've defined the luminosity function. Mm-hmm. The AS is the area of the survey. We said we're going to do a survey over 20,000 square degrees, so half of the sky. And then the 1 over epsilon, that's the observing efficiency. If we're only observing half of the time, it's going to take twice as long to do a survey. And so the key number here, I think, for most people will be this one, D, the size of the mirror. So it's a 280 meter diameter mirror with, and then the next number is the area of the focal plane. That's the AF. So we said a 20 square degree focal plane. So that's a pretty big focal plane in terms of area on the sky. But as we'll talk about later, if we're talking about that large of telescope with resolved pixels, it's really an enormous focal plane, tens of meters across of pixels. So this, of course, I think it's quite easy to see that a 280 meter telescope is an ambitious technical goal, but a 20 square degree focal plane that's tens of meters across is quite ambitious as well. So then the next equation, number in the equation is signal to noise. Yep. And then we have 2 fluxes. One is the FS, that's the flux of the sky. So what we've done is we put our fiducial telescope here at L2, the Earth Sun Lagrange point 2, beyond the orbit of the moon. But that's a reasonable place for space telescopes. James Webb Space Telescope will go there next year, Euclid the following year. The Roman Space Telescope will be at L2 later in this decade. And then the final thing is the flux of those objects. And so the things that are really uncertain here in terms of what we don't know is that F naught, the flux of the objects, and the A naught, the area of those objects, because we don't know where that luminosity function turns over. So those are the lever arms that nature will provide. Mm-hmm. So did you have a question or?
Nope, I'm with you.
Okay, so I'll continue. So let's go on to the next page. And so what this allows us to do is it allows us to make this plot. So what this plot is, it's giving us the, on the x-axis is the absolute magnitude of galaxies at the luminosity function turnover. And so, of course, to the right is making it harder and harder to get all of those galaxies. And then on the y-axis is the redshift at which those first galaxies are forming that are involved in well, not the first, but the galaxies at that turnover. Right. So up is more challenging. So our fiducial telescope is that plus. And as I said before, we've made a somewhat optimistic assumptions, and that is what we're showing on the plot is we think really the range of theoretical uncertainty that exists for the absolute magnitude and the redshift of where the luminosity function turnover would be. So this gives some idea of that range that's still unknown. And that's probably something that will become much better known, in a couple of years with James Webb Space Telescopes. Where we would need to be on this plot is not something that will take, I think, decades to know. It will obviously be decades before we ever build a 280-meter telescope, but we could know what the telescope required to do this survey as well before that. And so what we're showing here is the contour plot of the required mirror diameter to do this single band final galaxy survey that really extracts all the useful cosmological information from these galaxies. And so the plus here is at about 280 meters, which is the number from the previous page. Right. But it can go all the way up to 100,000 meters if the galaxies are much fainter and higher redshift. So right. There's a range. So that was the first science case we outlined. And the next case we outlined, and this is one we spent quite a bit of time thinking about, was galaxy evolution. Mm-hmm. And so this is a more open topic, I would say, than cosmology, because with the cosmology, we just say, what's the useful information in the clustering of galaxies? But for galaxy evolution, it's a little bit harder to pinpoint what the questions are, what the questions will be in the future. And so what we did here is we said that we would want a telescope that would be able to look at and resolve some of the earliest, faintest galaxies in the universe. And again, there's an uncertainty about when those galaxies formed and how bright they were. Right. So in terms of how bright they were, we took as a proxy some of the small dwarf galaxies near the Milky Way, like the Magellanic Clouds and so on. We said, okay, those would be, those on their own would be the earliest sort of proto-galaxies with maybe hundreds of stars. Okay. So we looked, through the literature and talked to some experts and said, when do those earliest galaxies form, and how bright would those earliest galaxies be if we tried to observe them? And as you might imagine, there's a huge uncertainty, but we did sort of the same thing that we did before, which was we made some assumptions about those. Right. Now, in doing the galaxy evolution final survey, we also didn't say we would need to study every galaxy in the universe at that redshift and that small. We said, all right, what do typical galaxy evolution studies need in terms of numbers of galaxies to get some statistical idea of how those galaxy properties are changing as a function of environment and so on. And right. So we said that we would need roughly 10,000 galaxies in each bin of redshift, and to get about 1% precision on whatever galaxy evolution question we are asking. So if we need 10,000 galaxies, then that allows us to say, okay, how big a survey do we need to get 10,000 galaxies? And of course, the answer there is it depends on what the surface density of those galaxies are.
Sure.
And so we made some assumptions, based on the literature about how distant and how faint those earliest galaxies that we'd want to study are. But when we did that, we found that within the literature, really, there was about 5 orders of magnitude uncertainty in the number density of such galaxies.
Okay.
So again, there's a huge range of possible values here. So what we did is we said, all right, let's assume it's logarithmically right in the middle of that range. So as an assumption. And so we did sort of the same thing that we did for cosmology. And we said, okay, what is the area of the telescope and the size of the telescope we would need to do a survey that answers these questions? And here we came up with a number, as you'll see in the second line there, that we need a 13-kilometer diameter telescope. Okay, so, in the previous section, we came up with 280 meters, and that's a thing of science fiction. But I and, people I talk to at JPL that are thinking about building things in space, they think, oh, in a few decades, maybe we'll be able to build things that are hundreds of meters across in space. But no one seems to want to talk about building a 13-kilometer telescope, optical telescope in space. Okay, so we put some more thought into it and said, okay, does this mean we'll never, or at least not for hundreds of years, be able to answer these questions in galaxy evolution? And the idea we came up with was, let's use the natural magnifying glasses that the universe provides.
Okay.
So that's gravitational lensing. So in order to see these faintest objects, we said, all right, instead of having to view them in their unmagnified form, let's use galaxy clusters, huge associations of dark matter, as gravitational lenses, and they will magnify these galaxies by about 5 orders of magnitude, making this problem somewhat more tractable. And the nice thing about that is when we think about the galaxy clusters, those are relatively close, at redshift 1 or even less. Yeah. So there's not a huge theoretical uncertainty in the number of galaxy clusters out there that we can use as these magnifying glasses, like there are in the theoretical uncertainty of the number of very faint or very distant galaxies. We know how many galaxy clusters there are. We don't know that exactly, but it's not orders of magnitude uncertainty. So, and it turns out that the number of galaxy clusters is sufficient over the sky to allow us to, with a small tweak on the cosmology telescope that we define, the 280-meter telescope, in a few days to a few months, do a much deeper survey using galaxy clusters with that same telescope to get the number of galaxies, these earliest proto-galaxies, we think we would need in order to solve these galaxy evolution questions.
So a question on the 13,000. That doesn't necessarily mean it needs to be a monolithic, right? 13,000. Could you run an array?
Yeah, exactly. And so and we have that built into the equation here. So if you look at that first line, if we want to keep the time at 10 years, there's this 1/n. So if you have
Okay.
in telescopes, the diameter goes as, square root of, sorry, the required diameter goes as square root of in,
Okay.
because in is in there linearly and the diameter is in there as d squared. So
Okay.
certainly you could imagine an array of telescopes. Yes.
I'm with you.
All right.
So here's our white dot on figure 2.
Yes. So it's similar to the other. So this is without the gravitational lensing. Our required telescope is absolutely enormous. But the gravitational lensing, I would say, allows us a way around this, and so allows this problem to be sort of theoretically tractable in terms of the numbers that we've been talking about for cosmology. All right, so if you go on to the next
Supernova.
Section 3.4, we said, okay, what does it take to study supernova? Because this is a big part of, for instance, what the Nancy Grace Roman telescope is going to do. It's going to look for supernova. And it turned out that this was, in many ways, really the simplest of these, in that if you get a sizable telescope, tens of meters, it's big enough to see just about any supernova that occurs where it's looking in the universe. So essentially what we found is that if you're doing this, for instance, cosmology survey, the first survey we talked about, and you're doing repeat visits of the sky to build up over that 10 years, to build up the numbers of photons you need, you're going to see the supernova. And so one of the interesting things about the supernova, of course, is that if they're at very high redshift, and we're talking about redshifts of beyond 10, the time dilation makes the supernova light curves, instead of days or months, it makes them years. And so the key here is you can't do a supernova survey that lasts for months if you want to get the full light curve of these very earliest and faintest supernova. You would have to do it over the course of years. But that's just the survey that we've defined in the cosmology part, is a survey that takes 10 years. So in a way, what we said is, if you design that cosmology survey cleverly, then you'll get these supernova for free. Right. I say get these supernova, you would get every supernova exploding anywhere in the universe that survey was looking. And if we're looking at half the sky, really you'd say we would see any supernova occurring in that half of the sky back to the beginning of the universe. So that to me was kind of exciting.
Yeah, very cool.
So that defined the telescopes that we would need. So then in section 4, where you're pointing now, we thought about, all right, what are the ways that we would build such a mission in the future? And so one of the key numbers, if you recall, was the sky background. And the brighter the sky, the longer we need to integrate on the object to get to a certain signal to noise. Right. And so what we found was that, and again, this is us looking in the literature, this isn't us some revelation that is from us. We're compiling work that's done by others. We found that you can get much lower sky background by a factor of 5 or more by going either beyond the asteroid belt, because much of the sky background is from zodiacal light scattered in dust in the solar system, or about 1 AU out of the plane of the solar system. So you just send the telescope, yeah, that's right, up. And so since we're in some far future where it's okay to think about making 280-meter telescopes, we said, all right, let's not have the telescope near the Earth or the Moon. Let's put it quite far out. And so what we're showing in this figure 3, this is again the required telescope aperture versus the sky background for 1 and 4 telescopes to do the cosmology survey that we defined in the beginning.
Okay.
So from the ground, you see with a single telescope, the sky background is so high that we need a telescope that's at best a kilometer, but could be up to many kilometers across. And the spread in those curves is, again, the spread in our uncertainty about the properties of those early faint galaxies that we would need to see. So the more challenging ones are if we put the galaxies fainter or further away.
Right.
And so at L2, which is where we put our nominal survey, you're getting to, in the middle of that red curve, about 300 meters, 280 meters, what we found before. But this line a little bit to the left of L2, the dotted vertical line, that's if we go to 1 AU above the plane. And so you can see that if you do that, you're getting to around maybe a 100-meter telescope that's required. Or if you were to build 4 telescopes, you have 4 telescopes that are a few tens of meters across. Now, in the era of JWST, a few tens of meter telescopes still sounds very ambitious, but it's sounding a bit more tractable, like a science and technological progress rather than complete science fiction. And so we're really trying to show that there are ways to make this more tractable. For instance, getting the telescope to where the sky background is quite a bit lower. Now, you will see that these curves keep going to the left, and we didn't talk about that much because the sky background, as you get to further than 1 AU out of the plane, is dominated by light from the galaxy. So getting to those lower sky backgrounds is not actually possible within the galaxy. So it's really that dotted line between 10 to the minus 3 and 10 to the minus 2 we think is sort of the best that we can do in terms of sky background. So then if we go back to the paper here, we would need an extremely large focal plane, and we're talking about here, for instance, we're talking about focal planes in the terapixels, trillions of pixels. What I've done here between equations 11 and 12 is I've actually chosen a 10-meter telescope. I've said, because that's the size, for instance, of James Webb Space Telescope. But if we had the huge focal plane, so the really idea here was to talk about how big the focal plane would need to be, even with a modest, comparatively modest size telescope. So we'd have a focal plane with a 10-meter telescope that's about 2 meters on a side. That's a number right there after equation 12. Of course, if we are then going to have a telescope 280 meters large, we'd have, as you see in that, we'd need about 60 terapixels. So an absolutely enormous focal plane. And so this is something I've actually talked to people, for instance, like at Teledyne, a company that makes astronomical detectors, and said, hey, I'm thinking about these things, and they said, hey, that's really cool, we should talk. So there are companies out there that are, I'm not saying ready to build this, of course, but they like to think about, so it's not just NASA that likes to think about these far future or decades away technology things. So we would need huge numbers of pixels. And then I do talk here a little bit, I reiterate that we are also assuming perfect pixels, which may be technically challenging as well. So I guess we can go on to the next.
The other interesting thing is,
yeah, go ahead.
Probably not part of this survey because we're going ideal, but what kind of time would it take to download from space 60 terapixels?
Yes, I actually do talk about that in terms of the um, uh, let's see if we keep I do talk about that in one more section. So 4.4 here is the extremely large aperture. How we talked about we needed a 280 meter telescope. Could be smaller if we get to a lower sky background area of the solar system. But then I talk about the data volume, and I talk about the data volume we would need if we had a certain number of terapixels and 16 bits per pixel. And so we do a quick data volume calculation. So a data transmission rate of 25 gigabits per second continuous. If for a 10-meter telescope, if we had a fleet of 10-meter telescopes, but if we have a single monolithic telescope, we would need about 800 times as much, or close to 1,000 times as much instantaneous data volume. So the only conceivable way to do this is through laser downlink of the data. And that's something, of course, that NASA is working on, optical communications. And optical communications over the solar system is something that, the links of the solar system. So, but what we would require here is, I think, a few orders of magnitude improvement in current systems of data downlink. So one of the things that we didn't think about here is what would it take to process, computing to process that much data and store it. It was really sort of beyond the scope of this, hoping that, Moore's law keeps giving us better and better computers. But we are talking about, 1,000 petabytes of data for this. So I think what I say here is we need multiple orders of magnitude in the data rate and about an order of magnitude increase in the range of the optical communication in order to accommodate these surveys. So that brings me to the end of the paper. The idea behind the paper, of course, was that we outlined, as I said, some science cases and how would we exploit the information in galaxies, all of the information in galaxies, to solve those science cases. And again, I do want to iterate, I'm not saying that's the only or even the best way to address these science cases. We were just talking about if you take the current era of galaxy surveys to its logical end. And so one of the things that interests me now is to pick out from here the technological tall poles. What are the hard things to do? Is it hardest to build that size telescope, or is it hardest to manage to downlink that much data, or have many terapixels? And I imagine it's challenging to do all of those, but I think in looking at those as end goals, we will advance those technologies in a way that gets us a lot of interim galaxy surveys and other science that's going to be really exciting. And so in the coming year, one of the things I hope to do is meet with some engineers and forward-thinking technical people at JPL and beyond, and say, here's where I'd like to see technological progress in the next 30 to 50 years to allow us not just to do this final galaxy survey, but to allow us to do the steps along the way. There will be other surveys before that.
Sure. And we'll learn from those and work toward those. That is pretty awesome. That's a nice, it's an idealized piece of work, but it's really lovely. It sort of, it puts the goalpost somewhere. It gives you something to strive for. So it's very cool. Very nice. Jason, I want to thank you so much for sharing that really lovely paper on the end of galaxy surveys and where we're going to go over the next couple of years with this.
I really appreciate you reaching out and having me on the show, and I look forward to, if people want to ask questions about this, I really look forward to feedback and talking to people about this. It's a really fun thing to think about, so I've really enjoyed it. So
Yeah, so go ahead and reach out. We won't be putting your email address in the video description below. Don't need that, but people in the game will know how to get you.
people
Feel
can
free,
find me.
reach
Yes.
out. It's a great topic. Awesome.
Well, thank you very
All
much.
right, Jason. All right, everyone. Thank you. And we'll see you on the next one.